Hey there, Calc 3 folks. I'm back here with another quick lecture over our study of infinite series, where we want to focus a little attention up now in section 10.7, where we are introduced to what I've kind of highlighted as a bit more of a what I might call hybrid tests of an infinite series for convergence. These are kind of unique in terms of these two tests and how they apply. I call them hybrid because really they work for both non-alternating and alternating series, folks. And in fact, they are probably going to be the tests that we rely on maybe a little bit more when we move into some chapter 11 material, where we'll be looking at the power series, and these tests are going to help us out a little bit in the study of power series. So it is just two more tests here, and I work in two examples of each, and they do present themselves very similarly in these theorems. However, there are really what we might point out some rather unique cases where these tests are certainly most applicable. And that should be obvious as we look at a couple of examples here, as well as what might become obvious as some of the ways that these tests actually work out, some of the practical algebra that happens within these tests. So we will jump into it here. What we do point out is these tests are used to determine what we call absolutely convergent behavior. And if we are absolutely convergent, we then can be considered convergent overall, right? And the first of these is what we call the ratio test. And here's the ratio test, right? It does start with the assumption that you just have an infinite series, right? We are starting off with assuming that our given series is just an infinite series, and it's not specific as being non-alternating or alternating. This works for both cases. It just has to be an infinite series. And along with that, we're going to let R be the value of this limit, where this limit is prepared, right, for an argument that involves the argument seen in our infinite series. This argument a sub k seen in our infinite series is used in the argument of this limit, where we are applying this limit as k heads to infinity to the absolute value of what is the ratio of a sub k plus 1 over a sub k. All right? And depending upon how r behaves, right, as k heads to infinity, right, will determine one of our three results for the ratio test, right? To begin with, if that value of r is less than 1 in value, as k heads off to infinity, right, the series converges what we say is absolutely, and thus must converge, right? Whereas if r is bigger than 1, which does include the case for r itself being an infinite limit heading towards the value of infinity, the series is what we say is divergent, right? The series diverges. And the one drawback to this test is the case where r equals 1. When r does equal 1, we end up with what we call an inconclusive result in this test. All right, so you will have at times these tests give inconclusive results, a lot like a few other tests that we've seen. At least the divergence test has been another test where we encounter some inconclusive result, at which point you would then maybe have to rely on other means to determine your behavior of the infinite series. Now, let's look at an example. All right. This example does kind of highlight the cases where this is certainly a very appropriate approach, right? If you take note here in this infinite series, we are looking at an infinite series that involves, first of all, we notice this factor -1 raised to the kth power, right? Where -1 to the raised to the kth power, we understand if it's a factor inside a series, is going to cause an alternating behavior. this series is going to alternate between positive and negative in value. Each term will. So, yeah, the ratio test is appropriate here, right? It can actually be applied here. This applies to any infinite series as well as alternating infinite series. The other thing we might point out about this series is this quantity right here, right? This quantity given by k factorial over 2 to the kth power, right? 2 to the kth power we're familiar with, right, as a functional type of behavior, right? That's, what do we say there, is a power behavior, right? A power of 2 behavior, right? Whereas k to the factorial may not be so familiar to us as a type of functional behavior, right? What we want to keep in mind is that k factorial, though, is a functional behavior where what we're describing here is a product, right? A product that starts at the value of whatever k is and is multiplied by the quantity k minus 1 times the quantity k minus 2 times the quantity k minus 3, all the way down until the last couple of numbers we're multiplying are the values 3, 2, and 1, depending on how large the value of k is. All right? We haven't really encountered this too much in our calculation of limits. We haven't really encountered a k factorial too much in our calculation of integrals, right? And some of the tests rely on those values in their calculation. So, yeah, our approach here, right, using the ratio test is certainly a little bit more obvious to be a natural in this case, because we do have this argument of k factorial within our argument of the infinite series. Now, I'll show you why here that is the case, and this does show up in the algebra, folks. All right? To begin with, in this test, we do point out what is our value of a sub k, and the argument a sub k inside of our infinite series is this value, negative 1 raised to the kth power times this factor k factorial divided by 2 to the kth power, right? Which does have an implication to it, and that is, first of all, in regards to the value of a to the k plus 1. A to the k plus 1 is going to be used in the numerator here of this value for the limit that we're calculating as the value of r, right? Where a to the k plus 1 is just the value of a to the kth, right? A sub k, where each value of k in that argument is replaced with the quantity k plus 1. So negative 1 will be raised to the kth plus 1 power. K factorial will become k plus 1 factorial. And 2 to the kth power will become 2 to the kth plus 1 in power. All right? And if we think about what would then be the argument of the limit given by the absolute value of a to the k plus, or a sub k plus 1 over a sub k, the absolute value for what we're going to find is the argument of this limit, right, is going to be given by this complex, what? Ratio inside an absolute value, right? The first thing we might point out, and to go ahead and get these out of the picture, the absolute values, is that the absolute value is going to, we might say here, cancel all of that alternating behavior we have occurring. The alternating behavior that we see is now occurring in the numerator, and this alternating behavior that's occurring in the denominator. This absolute value will distribute itself across quotients into the numerator and denominator, and any negative result that we encounter from these factors that cause the alternating behavior will be, in a sense, undone or canceled by the absolute values application. So to begin with, one of the things we're able to do, that you'll notice here, is those factors will eliminate with the absolute value symbols, right? And it will produce this complex form, right? We're to now begin evaluating this complex rational value. We can keep in mind that dividing a fraction by a fraction can be handled by taking the numerator and multiplying it by the reciprocal of the denominator here. And that's what we have in our next step, is we do show that this complex rational form can be rewritten by multiplying by the reciprocal of our denominator. All right? Now, this quantity here, our result, can be simplified a little further. And I do bring that into note here. Furthermore, we might note, when we think about the quantity k plus 1 factorial, it does give us the result k plus 1 times k minus 1 times k minus 2, where this pattern continues all the way down until we get to our last three factors of being times 3, times 2, and times 1 in value. Right? Where, if we spend just a moment there and take note, another way to think about k plus 1 factorial is actually just having the value k plus 1 times everything else, where everything else can be thought of as just being the result of k factorial. So another way to rewrite k plus 1 factorial is to understand it as really just the value k plus 1 times k factorial. That's going to be convenient here in a moment to start simplifying this result. You might see how that would apply. But let's also note, for this quantity 2 to the k plus 1, one way that it can be simplified is by realizing that this sum of k and 1 in the power is a result of multiplying 2 times the quantity 2 to the kth power, right? The product here involves two powers, right? 2 to the first times 2 to the kth, right? If we think about this, this is actually 2 to the first power times 2 to the kth, where, right, how we multiply these two powers of 2, these two powers that have similar bases, is we can add their exponents, right? And that is what we have occurring here, all right? So we might go ahead and kind of highlight that in this middle step, all right? Being able to rewrite 2 to the k plus 1 found here in this denominator as 2 to the times the quantity 2 to the kth is certainly going to be a bit convenient here, you'll notice, right? In fact, if we begin to set up that understanding, right? So if we begin to think about that absolute value that we had back that we had before this furthermore note, right? We might note that this quantity that we had as our result there, right? This quantity here can actually be rewritten, right? Using what we had noted. If I bring this up into view, right? As we had noted, that quantity k plus 1 factorial can be rewritten as k plus 1 times k factorial. And this quantity in the denominator here, 2 to the k plus 1 power, can be written as 2 to the 2kth power. Right? Where when multiplied by this reciprocal of the denominator, we can now note that in that numerator, 2 to the kth, will cancel with that 2 to the kth found here in the denominator. And this k to the factorial found in this denominator of the reciprocal will cancel with the k to the factorial we have here in the numerator, right, in this simplified nature of k plus 1 factorial, right? This k factorial in this numerator will cancel with that k factorial in that denominator. With those common factors canceling, what you're left with is just the quantity k plus 1 divided by this factor of 2. All right? The absolute value of a sub k plus 1 over a sub k is just the quantity k plus 1 divided by 2. So what we're going to now do is actually calculate r, which applies the limit to this. right? Which is going to apply the limit as k heads to infinity to this, which you can already note what that result is going to be. We've done all the algebra above here, right? And when we think about the value of r then, what is the limit as k heads to infinity for this absolute value statement, right? It would just be the limit as k heads to infinity for k plus 1 divided by 2. Whereas k heads to infinity in this numerator is going to head to infinity, and simply dividing by 2 is not going to change that behavior. The overall behavior here is heading off towards infinity, right? And thus, we might point out, since r, right, approaches the value infinity, it is a infinite limit, right? By the ratio test, this infinite series S is divergent. Right? This infinite series S is going to be a divergent series. All right? That is our result given in the second result, right, for this what we call ratio test. Much of our time was spent simplifying this absolute value, but once I had a nice simple form there, just that k plus 1 divided by 2, the limit of that was simply infinity, right? It's heading off towards infinity in value, so we must be able to conclude that this series diverges. All right? That's one example. Let me do another quick one for you, where I've gone a little too far. Let me bring this into view. Or consider the behavior of this series. All right, this value of S. All right, you take note in that value of S. Again, we might first point out what is our argument here. All right, the argument a sub k in this case is k cubed divided by 5 to the kth power. Implying if we think about what is the value of a sub k plus 1, every value of k we see in the argument a sub k, this value of k being cubed, and this value of k playing the power on the power of 5, are going to get replaced with k plus 1 in power. Where, in the numerator, k plus 1 cubed, we might just leave as our understanding k plus 1 cubed. But as we saw in our previous example, a power, right, raised to the exponent of k plus 1 can actually be rewritten as that power times the power raised to the kth, right, exponent. So that's 5 to the k plus 1 power, just like in our previous example, we might go ahead and simplify as 5 times 5 raised to the kth power. All right? And if we think about then the absolute value of a sub k plus 1 divided by a sub k, right? The absolute value of a sub k plus 1 divided by a sub k would set itself up again in this complex absolute value, right? Where to eliminate the absolute values, this is a non-alternating case, folks. In our series, k is always going to be from 1 up to infinity. K is always going to be greater than 0. It's always going to be positive. So if we go through this real quick, we might just note k plus 1 cubed will always be positive because k plus 1 will always be positive since k is always positive. Since k is always positive, 5 to the kth power will always be positive times 5 will always be positive, right? And we see similar behavior down here in the denominator. We'll always have a positive divided by a positive, so this overall argument inside the absolute value will always be positive. So the absolute value symbols really just are not needed because the argument on the inside is always going to be a positive result. So we'll go ahead and drop them. That's our argument for being able to drop them there. And then as we've done in our previous example, instead of the complex form here, let's multiply by the reciprocal of the denominator. And we prepare this statement. Where a lot like the example before, we do see these 5 to the kth powers canceling with each other, right? Leaving us with this result here, which does not simplify much further, folks. Expanding k plus 1 cubed, you might consider doing that, but I will tell you, what we want to think of is, remember, always keep in mind what we want to do with this is we want to apply a limit. And what we're trying to do is prepare an argument where we can apply the limit and see the result of the limit rather readily. All right? That may have not been so easy to do here, or even more easy to do back here in this complex form. But now at this point, I think we can apply the limit rather readily. Right? So if we think about the limit being applied here, and we think about our value of little r, so little r, right, will just end up being the limit as k heads to infinity, right, for what is this quantity, k plus 1 cubed divided by 5 times k cubed, which we notice, folks, is just the limit of this rational form. And we can go back to our fundamental rules of limits at infinity for rational forms. And what it says to do is to analyze your powers, right? Or I should really say your degrees of the numerator and your degrees of the denominator. And what we notice is, and really it's involving considering the end behavior of this rational form, where what we do notice is this k is going to have a degree of 3, and this k has a degree of 3, right? Where that tells us the limit's value is going to be the ratio of the leading coefficients for the polynomials found in the numerator and denominator. And if we think about this polynomial in the numerator, it's going to have a leading coefficient of 1. As for the polynomial found in the denominator, 5 times k cubed, it's going to have a leading coefficient of 5. So the ratio of 1 to 5 is simply 1/5. Right? The value of r here, right, is really just the value of 1/5 in value as a limit, relying on some rather fundamental techniques in our evaluation. All right? Note, the Hopitals Rule will also get you that result, folks. The issue with the Hopitals is you would have to apply it 3 iterations, right, for 3 iterations. And that can be a bit tedious. Right? We're relying on our fundamental rules, makes it a little nicer. So that's our value of r. And if we keep in mind, what does that tell us? Well, thus, since r, which equals this limit here, equals 1/5, right, in value, which is less than 1 in value, by the ratio test, this series must be absolutely convergent, right? And thus, we might point out, convergent. And also just convergent. We might say that, right? So folks, that's 2 quick examples highlighting the use of this theorem known as the ratio test, right? I tried to give you some good examples that illustrated this, really the appropriateness of when this test applies. And a lot of it has to do with, first of all, not having really any other means to begin evaluating this this series, right? We really encounter that here with perhaps the case of a factorial in our argument, right? But then I also tried to highlight some of the algebra that happens nicely in these tests, right? Which leads to being able to calculate this result for r in a rather nice manner, right? And as I had highlighted, these tests are really going to be useful for us up in the, or really specifically even the ratio test is going to be extremely useful for us up in the study of power series. And specifically the Taylor series is where we're going to make use of, I think, the ratio test, if I recall correctly. All right? But what I am going to have to come back to, folks, is another quick, well, we have to look at the second half of this section, 10.7, the root test, which is, again, is a very similar looking test. What is going to be different, though, is the limit that we're going to be calculating back here, right? Other than that, the test is going to have very similar results in its application, right? So I will be back with that example, well, that set of notes here very shortly. Hey there, folks. Back with the second half here in our lecture over the ratio and the root test, where we want to spend a little time with the root test. And as I've highlighted here, or in the first half, at the end of the first half, is that the root test is going to look a lot like the ratio test in terms of its layout here, right, and the results of the test. Where we do see a bigger difference, though, is over here in the argument of the limit we're calculating, right? Which in the root test we are going to define as a different value as our test. What would we say this is? This is our test value, right? This number rho, right, or this variable rho, is now going to equal this limit as k heads to infinity for what is the kth root of the absolute value of a sub k, right? That is going to be the test number used in the what we call root test. And depending on this value of rho, we will see different results, right? One of three different results, all summarized down below here. Very similar to the results that we saw in the ratio test. If rho is less than 1, series converges absolutely and thus converges. If rho is bigger than 1, including the case where we have a limit or an infinite limit here, rho heads to infinity, the series diverges. And if rho equals 1, the test is what we consider inconclusive. All right, take note, folks. So let's look at our first example. Bring this up into view here. Certainly you can kind of hopefully start to recognize when this might be appropriate. And we can see that here perhaps in the argument of this series, right? Consider the behavior of this infinite series S, where S is this infinite series that involves this quantity, which does involve this negative, and we'll come back to that in just a moment, but more so this quantity raised to this kth power. What we might point out is that taking the kth root of something to the kth power is a rather convenient approach, right? We might begin by indicating here, in this case, our value of a sub k is this argument, right, that we see inside our series, implying if we thought about the kth root of the absolute value of that argument, that would give us this result here. We could take the kth root of the absolute value of this produces this. Where we might take a moment just to kind of highlight how we're going to handle this negative here. This negative is a -1 being multiplied by this ratio 2 times k divided by k plus 1, right? And that -1 here, along with the ratio, is being raised to the power of k. And that power of k will distribute itself across products. So that power of k can distribute itself to the negative out in front, this negative here, and become -1 raised to the kth power. And the quantity 2 times k divided by k plus 1 can have the power of k applied to it also, right? That k will distribute to both those factors, right? Now, the absolute value will cancel with this -1 raised to the kth power. What we can note is that is a hidden, right, alternating factor. That is the factor that's going to cause an alternating behavior in this series. If we were to lay out the terms of this series, we would likely see those terms would alternate. All right? The absolute value will cancel with that alternating behavior, leaving us just with this quantity here, which will always be positive for values of k equal to 1 and beyond. All right? So then if we take the kth root of this quantity raised to the kth power, the kth root and the kth power are now going to cancel, leaving us with this result 2 times k over k plus 1. If we come back now and consider that as the argument of our limit, and consider the value of rho equal to the limit of this result, right, is going to be the limit as k heads to infinity for 2 times k over k plus 1, which is the case for a limit at infinity of a rational form, and relying on that rational form and some understanding of how the end behavior will behave for this rational form. We note that because the degree of the numerator and the degree of the denominator are both the same, the value of this limit at infinity is given by the ratio of the leading coefficients. In the numerator, we have a coefficient of 2 that leads, and we have a coefficient of 1 that leads in the denominator. So 2 over 1 simplifies to the result of 2 here. All right? So the value of rho in this case is equal to 2. And since rho equal to 2 is greater than 1, the result of the root test tells us that series must be divergent. All right? So that is going to produce a divergent result here. Again, that is the root test. A big part of the test happens here as we attempt to simplify this argument seen in our value known for as rho, right? The argument of this limit is we often have to be able to begin simplifying that so we can actually evaluate the limit. And that really is the tricky part of these tests. But once we get a nice version of that argument of the limit, right, evaluating the limit shouldn't be too tricky. Well, I say that before we see our last example here. All right, what we do want to remember, there are some other rules that help us evaluate limits, and one of those is the case for the Hopitals. What we might encounter in some of these limits are what we call indeterminate forms. So we got to be on the lookout for those. So I'll roll through a little bit of Hopitals with you here in this next example. If we look at this particular series, what we have here is an infinite series where we're taking this quantity 1 minus 1 over k and raising that to the power of k squared. Now, here you might say to yourself, all right, I do have this power of k, but it's actually a power of k raised to a power of k. It's this k squared power. All right? We can use root tests to handle this case. All right? To begin with, in this case, a sub k would be equal to that argument we see up here in our series, implying if we thought of the radical for its absolute value, the kth radical of its absolute value, that would be given by this quantity here, where we would note that, first of all, this is always going to be positive for any values of k from 1 to infinity, so the absolute value symbols are really not needed. We can just drop those away. And then if we take the kth power of this quantity raised to the k squared power, one of those powers of k up here, this is what we might say is a k raised to a kth, the outer kth power of this quantity will cancel with this root of k, leaving one power of k behind. This is 1 minus 1 to the kth power as a result, where we now have to come down and consider applying the limit to that. And you go, well, the limit applied to that shouldn't be too tricky. In the denominator here, or I should say in the argument, this 1 over k. If k heads to infinity, this will turn into 0, meaning 1 minus 0 will become 1. But then all that is going to be raised to this power of k still. That's going to head off to infinity. The result, we can start to see, is actually going to be 1 to the infinite power. All right? If we consider the value for rho here, it is telling us at the moment that that is 1 to the infinite power, where some of you might try to argue that is the value of 1. We have to be careful with that. In the result of a limit, right, if we obtain 1 to the infinite power in a substitution, we have to understand that that is what we call an indeterminate form. And we need to apply, in this particular case of the indeterminate form, what we call the Hopitals methods for the case of the result 1 to the infinite power. Right? Since rho gives us 1 to the infinite power as this result for the limit, rho in the Hopitals methods must be equal to e to the lth power. Where what is L? If we go back to the methods, you might recall L is going to be the limit formed for what was our power in the previous limit, right? It is going to be the limit formed for k heading to infinity for what would be this power of k. That's seen as our first factor here in this limit, times by what would be the natural logarithm of this argument. What we're doing here, in a sense, is an exponential transformation, recall, in our Hopitals method. All right? It's going to be this power of k times the ln of this argument in our method. That's going to be the limit we're interested in finding for the value of L. Now, if I use a little substitution, this k will become infinity. 1 minus 1 over k we know is going to be the value of 1. So this is going to give us the L infinity times the ln of 1. Now, ln of 1 is equivalent to 0. So the end result is actually, infinity times 0, right? Where some of you might try to argue that's 0. Be careful. That is another indeterminate form, right? This is another indeterminate form, infinity times 0. And to approach the value of L then, from more Hopitals methods, I want to consider rewriting the argument of this limit so that it produces a result where I can apply the rule. And here I can do that by defining this natural logarithmic argument factor by the reciprocal of k, 1 over k. Now when I evaluate the limit of this as k heads to infinity, again, this numerator becomes 0, but our denominator also heads to 0. Where in the indeterminate form 0 over 0, we can apply what's called the Hopitals rule. All right. What is the Hopitals rule, if you recall? The Hopitals rule says, well, the limit you're interested in can be considered the same limit, right, the same value as the limit for what is the derivative of the numerator and the derivative of the denominator for your independent variable. In this case, our independent variable is k. So I'm going to take the derivative of this numerator, the ln of 1 minus 1 over k, and I'm going to take the derivative of the denominator, 1 over k, and that's going to be the application of the Hopitals rule. Where if I evaluate each of these derivatives individually in the Hopitals rule, we will note that the derivative of the numerator will turn into this quantity here. It is going to be 1 over 1 minus 1 over k, that quantity, times k squared, all over the derivative of the denominator, which would be negative 1 over k squared. Where if I set this up now in this complex form as a product with the reciprocal of the denominator, I produce this statement, where we can see the k squared and the numerator and denominator are going to cancel, and we produce this argument here, negative 1 over the quantity 1 minus 1 over k. If we evaluate that as our limit, well, the limit as k heads to infinity for our value of L here, we will then see that as that k heads to infinity, 1 over k will head to, again, 0. 1 minus that, 0, will be 1, and 1 over 1 is also the value of 1. So with that minus out in front, this result is negative 1 in value. So L is negative 1, and remember what L is. L is this power that we're going to place on E in our result here for rho that comes from the initial application of L'Hopital's method for this indeterminate result 1 over infinity. That L of negative 1 says that rho is now going to be equal to e to the negative first power. All right, here's our value for that L, implying, in the end here, rho then equal to e to the L must be equal to e to the negative first power, which if we think about that, that's just 1 over e. That's 1 divided by about something that's 2.72 in value. Well, 1 divided by 2.72 is less than 1. So rho, since rho equal to 1 over e is less than 1, by the root test, this series is convergent, right? It's absolutely convergent and thus is convergent, right? We know we're dealing with an absolutely convergent series here, right? It's convergent, well, I should say is, let's just go with absolutely. Because again, it is a alternating series. So we might be a little more specific here in calling out it as absolute, all right? So, folks, that is 2 quick examples of the root test. It does have results very similar to the ratio test, except the test value, the test number we're using, involves a different argument in our limit. We've certainly seen here the cases where it seems applicable, right? When you have these arguments in your series raised to this kth power, this will certainly be an approach you might consider, right? But you do also want to keep in mind as you work through these, you are calculating limits, so you're going to have to at times be prepared to encounter these indeterminate forms along the way. So I went ahead and worked through this last example, giving you a little highlight of, again, some of those familiar indeterminate forms. Those are going to appear in this work, folks. You want to be prepared for those. All right. With that said, I hope you're all doing well. This really does conclude the last lecture I had planned for Chapter 10. You will notice there is one last section in the book that talks about choosing a convergence test. With respect to choosing a convergence test, folks, it does start off with a little trial and error. It's a lot of it is experience. As I've kind of pointed out with the ratio and root tests and with the tests along the way, there is some kind of natural forms that appear that make it a little bit more, one test more appropriate than another. What I often tell students to begin with is the divergence test. If you're dealing with a non-alternating series, you might approach it with a divergence test. If the divergence test comes back inconclusive, meaning that it equals 0, the limit of the terms of the series equals 0, and you get that inconclusive result, you might ask yourself, well, can I then integrate it? Is it a series where if I thought about its arguments of k as an explicit function of f, would I be able to integrate that indefinitely, right? Perform one of those improper integrals on that, starting from the lower bound up to infinity. If you're not able to integrate that argument, what you might consider then going on to do is a comparison test or a limit comparison test, where in the limit comparison tests, certainly you're going to calculate a limit, an integral, right, in that calculation. If we go back, so again, there's some appropriateness there. If you can get it to become a calculation, you can calculate. In the comparison test, the comparison test alone, you might be looking for, can I compare this to a known series, some series that I know is similar in behavior, right? And then, if all else fails, you can come back here and try some of these root and ratio tests, folks, right? I will tell you that the ratio test is certainly going to be, and the root test might come into play as we look into some of the further studies of series in Chapter 11, though, where we are going to be studying the power series and particularly the Taylor series. And that's where I plan to come back in terms of videos, folks, is up there in Chapter 11. So hopefully you've watched all these videos over Chapter 10. If not, you want to make sure that you give them a good watching before you maybe consider jumping up here into this Chapter 11 material. All right? I hope to see you all then. I am excited. Yeah, this Chapter 11 has some interesting stuff going on in it, and I hope I'm able to share some of that with you. All right? So, hope you're doing well. Hope you're hanging in there. And if not, get a hold of me, folks. I'm looking for you all at some point in time to be working with me one-on-one or as a group in that collaborate. So, I'll hopefully see you there. Talk to you later.